How can we then find the linear regression line? The linear regression line is the line that best fits the data. If we look at the plot, we see that we have the observations marked in green, the line is given in blue, and in red are the distances between the observations and the predictions. What we want to do is we want to minimize the total length of all the red lines. To do this, we will look at the squared differences between the observations and the predictions. We will do this for all data points, so we sum over I is 1 to n, and then we minimize this function with respect to alpha and beta. Why do we want to square? Well, we square because in the end, the distance, the value of the distance is important, but not the sign. So whether or not the difference between the observation and prediction is positive or negative doesn't really matter. We just want to make this difference as small as possible. If we look at it mathematically, so we would get a sum of observations minus predictions. This sum is always 0. We cannot find values of alpha and beta by minimizing over 0. So how do we work out this minimization problem? We take the derivatives. So we take a derivative of L with respect to alpha, we set it equal to 0. We take a derivative of L with respect to beta, and we also set it equal to 0. Some easy calculations give us then equations 1 and 2. From equation 1, we can easily find that alpha is the average of y minus beta times the average of x. If we then combine 1 and 2, we can also find an expression for beta. To do this, we will apply a small trick. So we will look at the derivative of L with respect to beta minus x bar times the derivative of L with respect to alpha. Each of those derivatives is 0, so the combination of both is still 0, and this x bar is just a value, so we can put it in the sum. If we place it inside the sum, we get the expression on the right. In the next step, we then replace alpha here with the expression we found in number 3, and we get the value or the expression at the bottom of the slide. This expression only depends on beta, and so we can take out beta, and here we find an expression for beta, which is only depending on, or which depends on all the values of y and x. If we then replace y and x with the observations, the actual observations, we find an estimate beta hat for beta, and with beta hat we can also find an estimate alpha hat for alpha. Let's then go back to the example. So in our example, we wanted to predict the basal area in function of the riparian density. So what we do in R is we apply a linear model, so LM for linear model, where we say that the explanatory variable x is the riparian density, so the density, the tree density, and here this one, the basal area, is the outcome or the dependent variable. What we always do is we have a tilde in between. So to the left of this tilde, we have the value that we want to explain. On the right, we have the variables that we use to explain the y value. So if we then look at the model through summary model, we get estimates for the coefficients. We get an estimate for alpha here, which is minus 77.09908. We get an estimate for beta, which is 0.11552. So with these estimates, we can then also find the expression for the model. So our model, the average outcome is minus 77.10 plus 0.12 times x. So on average, the basal area is minus 77.10 plus 0.12 times the tree density. Other things that we get in our summary is a standard error for the coefficients. So with this standard error, we can find confidence intervals, and we also find here a t-value and a p-value. T-value, p-value, they are corresponding to, of course, a t-test. And the t-test that we have in this case is testing whether or not the coefficient is equal to 0. So we get basically here, for the second one, the null hypothesis is that my density, so my beta, is 0 or is significantly different from 0. In this case, we see that the p-value is extremely small, so it's smaller than 5%, and so the beta hat is significantly different from 0, and the model is a significant model. For the intercept, the test doesn't make any sense, because if we have a slope, we will always have an intercept. So we only have to look at the values for the riparian density or any other explanatory variable, but we will never look at the value, the t-value or the p-value for the intercept. If we then look at the interpretation of the model, we can say the following. So if we have, in this case, a basal area, which is given by the model, so minus 77.10 plus 0.12 times x. If we then take an increase of 10 in the variable x, so we have 10 more trees per kilometer, so x, or basically delta, is 10, then we see that the expected basal area increases with 1.2 square meter. So we just look here at beta times delta, so this is from here. So we see that if we have 10 more trees per kilometer, the basal area increases with 1.2 square meters. If we want to use it for prediction, we can do that also. So what would be the basal area if we have 1,600 trees per kilometer? We just plug in the value 1,600 in the model, so here, and we get an outcome of 108 square meters. So for 1,600 trees per kilometer, we expect that the basal area is 108 square meters. We can do the same for 500 trees per kilometer, but however, if we do this, we find that the average expected basal area is minus 17 square meters, which is quite strange because an area cannot be negative. So this is due to extrapolation. So 500 trees is outside the range of the observations. So the smallest observation that we have in our data set was 800. And 500 is smaller than this one. So basically we are extrapolating our data, or we are extrapolating our model outside the range of the observed data. And we always have to be very careful with it because we cannot verify the assumptions. So if we want to make predictions, predictions are only accurate if the value for which we want to predict lies within the range of the data that we observed. So we said it's a linear model. We took the assumption of linearity. We also have to check this assumption. The easiest way would be through a scatter plot. However, checking through a scatter plot is very difficult. So in this case, we have very little data points, and it's very difficult to say whether or not the association between them is actually linear. Also, if we have more than one explanatory variable, we can no longer make this plot. So it doesn't really make sense to base yourself on a scatter plot to verify linearity. So what we will do is we will rely on a residual plot. A residual is nothing else but a prediction error. So basically, it is yi minus yi hat. So it's the difference between the observation and the prediction. If linearity is true, then if we plot these residuals versus either xi or the predictions, then that plot may show no pattern. So if we take a scatter plot, we put the residuals on the y-axis, and then on the x-axis we either plot x or we plot the predictions. Then it means that we cannot have a pattern, so it must be approximately a horizontal line around the origin. So, how can we verify this? Well, we already made the model. We saved the model in model, and then we can also plot the model. So this one, par MF row, just tells R that we want to make the plots in a 2 by 2 matrix. So 2 rows, 2 columns. If we then plot the model, we get the following. So here we see we get 4 different plots. The one that is important for us at this time is the upper left one. This is the residual plot So on the y-axis we have the residuals, on the x-axis we have the fitted values or the predictions. So in this case we have y hat I in function of ei. If we now look at the plot, we see that the plot doesn't really show a pattern and that the assumption of linearity seems very plausible.